we still have to then remove a good amount of carbon dioxide from the atmosphere. Different mechanisms for the different materials.
How exactly is this building materials capturing this carbon?
We also know that building materials contribute a lot to emissions. 16 billion tons is reflective of global building materials. It's sort of like a double benefit.
Welcome to the Sustainability Nugget podcast. I am Rarasu Maraibi.
And I'm Tosin Folorunsho.
On this podcast, we learn about sustainability by discussing various related topics while focusing on three pillars: the economy, the society, and the environment. Hello guys, welcome back to the pod. So, a recent study was recently published in Science on how building materials could store more than 16 billion tons of CO2 annually. That's up to 50% of CO2 caused by human activities. So how exactly can this happen? Like using bricks or concrete or wood to actually capture CO2. Today on the pod, we have Elizabeth Van Rooyen, who is the first author of this study, and she's going to be breaking things down for us to really make us understand how exactly this can happen and answering all our questions. So hello, Elizabeth.
Hello, Rarasu. Thank you for having me.
Yeah, welcome to the pod.
Excited to be here.
Yeah, so let's just jump right into it. So before we start, can you please introduce yourself to everyone?
Yes. Hi, I'm Elizabeth Van Rooyen. I recently finished my PhD in Civil and Environmental Engineering at the University of California in Davis, which is where I conducted this research. And I'm now a postdoctoral researcher at the National Renewable Energy Lab.
So Elizabeth is actually my friend and colleague. So since we're talking about this paper, can you just give us like an overview of your study and like the key findings?
Yeah, so the goal of the study was to see how building materials could act as a form of carbon storage. And we primarily looked at really common building materials, so concrete, brick, wood, plastics. And we found that if we maximize carbon storage potential in these materials, we can store over 16 billion tons of CO2 per year. And that's just for newly built materials. So this isn't existing infrastructure.
Nice. So what inspired? Yeah, I know like it's quite glaring what inspired, but I want to know your inspiration to like go down this like study path, because we know about carbon capture, but we don't really hear much about like the building materials. So what's inspired this?
So we know that every year the window of opportunity to mitigate climate change and stay below certain climate targets gets smaller and smaller. And the recent IPCC reports show that in addition to really rapid decarbonization and reaching net zero emissions, we still have to then remove a good amount of carbon dioxide from the atmosphere in order to stay below these targets. And there are a lot of technologies that people are looking at for carbon storage, like storing CO2 deep in geological reserves or in oceans. But we wanted to look at how we can leverage existing infrastructure and materials as a form of carbon storage. And building materials, we produce a lot of. We're going to continue to produce them as population grows, and we use them for a long period of time, which can help you utilize that carbon storage. And on top of that, we also know that building materials contribute a lot to emissions. So if we could not only eliminate those emissions from building these materials, but then also store CO2, it's sort of like a double benefit. So that's why we were excited to investigate this.
I say two-phase, no, not two-phase per se, but like actually trying to make the building materials net zero, because we know like cement, right, is very like
huge emitter.
Yeah. So you're trying to bring it to net zero, but even put it further to like negative, carbon negative, to store like the CO2, right? So when I think of carbon capture and all, like you have the direct air capture or like capturing at like the source, What I know is, like you said, either they're capturing it and putting it down in geologic formations, or maybe like converting it to products like fuels. And so now, like, I'm thinking, is this CO2 being converted to building materials, or like how exactly is this building materials capturing this carbon, basically? Yeah.
Yes, that's a great question. So the focus of this study is more on the carbon storage aspect. In order to store the carbon in these building materials, you also need a source of CO2. So in order to achieve those IPCC targets of removing CO2 from the atmosphere, that would have to come from something like direct air capture. Or another thing that we look at a lot in this paper is the use of biomass, which would also be a form of carbon capture through photosynthesis. But the bulk of the carbon storage in this study is coming from carbonate-based aggregates, which is basically the rock or gravel that make up concrete. But instead of using regular rocks, you're basically creating synthetic rock by reacting mineral oxides like calcium oxide or magnesium oxide with CO2, and then forming a calcium or magnesium carbonate. So that CO2 becomes chemically bonded to these materials and is a very stable form of carbon storage. But like you said, you still need that source of CO2. So yeah, either from the atmosphere or from industry, flue gas. But that technology still has to be developed.
I think I need to visualize it better. So, like, I know you just talked about the reaction forming the carbon aggregate, but how is that being added to wood, for example, or brick or
Right.
whatever?
So there's different mechanisms for the different materials that we look at. So for the carbonate-based aggregates, carbonatable cement and carbonatable bricks, those are all a similar process of reacting CO2 with an oxide to form the material. But we also look at just a 20% increase in wood consumption in building materials, which is in line with projections for how we're going to increase wood consumption. And then for plastics, for example, we're looking at bio-based plastics, which is just, converting biomass into polyethylene or PVC. And then we also look at using biomass fibers in brick, up to 15% replacement of brick, and also biochar in cement. So yeah, there's sort of the biomass side and then like the carbonatable materials. There are sort of two different mechanisms.
Okay. So in all of like the materials like you looked at, which one has like the greatest carbon storage potential?
So that's actually a really interesting question, because if you just look at the materials on a per kilogram basis, plastics have the highest potential for carbon storage just because of the really high carbon content. But if you look at the mass of plastics versus something like concrete, it's a drop in the bucket. The concrete aggregates are the greatest potential for carbon storage on a global scale just because we consume so much of it. So just the aggregates, I think, amounts to 11 billion tons of CO2. So 11 out of the 16 is just coming from that one material.
So like you're looking at it based on how much is being used now, but like did you scale up like, okay, plastic has the greatest potential, but can it be scaled up globally? Was that?
Yes. So when we looked at the future projections, we initially made a conservative estimate that we don't change the growth in demand of materials, because we didn't want to overestimate the potential for carbon storage, but there are a lot of projections that building materials are going to increase, but there's also a chance that maybe we're able to reduce demand if we, engineer our buildings with less materials or extend the use phase. So we did do sort of a sensitivity to look at the change in demand. And particularly for plastics, since they are expected to grow triple by 2050, the total carbon storage potential of plastics, I think, went from being like 1% to 5% of the total carbon storage. So still not a lot compared to aggregates, but there definitely is room for some growth there.
So again, like the carbon aggregate, this for concrete, right?
Yes, and also asphalt. So we also use a lot of rocks and stuff to make our roads.
So, we talked about how like the industry is already, correct me, cement is used in concrete, right?
Yes, correct.
Yeah. So it's already very emission like
intensive.
heavy, yeah. So how are you cutting it to net zero before even capturing carbon? Like, I want to understand the analysis. Like, what is bringing down that emissions before we're even looking at negative emissions?
Yeah. So the traditional way that cement is made is there's a chemical reaction, the calcination process actually releases CO2. So just producing a kilogram of cement, even if you were to use completely renewable energy and everything, you would still have CO2 emissions just from the chemical reaction. So the two alternative cements that we were looking at is magnesium oxide cement and then calcium silicate cements. And both of those would be a different chemical reaction where you're actually reacting CO2 with the magnesium and the silicates. The thing with the cement is, so like the concrete aggregates, you're forming a rock, it's the same as the rock you had before. There's no problem with performance. These carbonatable cements, because of that carbonation reaction, the pH of the cement is actually too low to protect against steel corrosion, which is really important for reinforced concrete, which we do use in a lot of our buildings. So for the carbonatable cements particularly, there would still have to be research on, maybe how to modify their performance. For now, I guess use it in low load bearing applications would probably be the best option.
Okay. Then what does you said you mix biochar in it, right? And
Yes, that was another thing we looked at.
So what does that do? Like, is that just biochar itself is a sink? So is that where?
Yeah, so the biochar is already a carbon sink because it's the CO2 from the atmosphere from photosynthesis. And what we're doing is just assuming that we can replace up to 15% of cement with biochar. So basically just using less cement and replacing it with this sort of carbon negative material. And there are some studies that looked at how up to 15% replacement could still perform similarly to regular cement. So that's why we chose that.
Okay. So, like in storing of CO2s, normally there's this concern about how long it can be stored, like, because even if you store it underground, it can be released. So for CO2 stored in these building materials, what's the risk of release over time?
Yeah, so this also depends on the material. So obviously, for example, just using wood in a building, that's not a very long-term storage because the wood could be burned at end of life and that CO2 can be re-emitted. Similarly with plastics, unless they're managed properly at end of life, they could be incinerated and again release some of that CO2. But for the bulk of the carbon storage, which is these carbonate-based aggregates, which make up 11 billion tons of CO2 storage per year, that CO2 is bounded chemically to the material. So these carbonate, calcium or magnesium carbonate rocks are extremely stable forms of carbon storage. And, even if you were to demolish the building at end of life and crush up the material, it would still be holding that CO2. Yeah.
Okay. That's a really long time.
Yeah.
Okay. So if we were to compare like in cost with and efficiency with conventional building materials, how does this look like?
Yeah, so we didn't do any cost or economic assessment in this paper. However, I can say that the current cost of aggregate is super low because it's basically just gravel. And right now, the cost of carbon capture, for example, is really high. So if you were to try and do this today, I would say it definitely would be more expensive than your traditional aggregates. Similarly, for like bio-based plastics, for example, petroleum plastics are super cheap. So it makes it really hard to be cost competitive. However, I think in the long term, if these technologies are scaled up and made to be more efficient, there's potential for it to be cost competitive because all of these materials are using basically waste materials. So like your carbonate-based aggregates, you can use mineral-rich waste streams from industry, from steel production. And for plastics, you can use, agricultural residues, which are also really low cost. So the feedstocks are low cost. There's a potential for it to be, but right now, especially just with the cost of carbon capture itself, these materials would be more expensive.
So yeah, you did just like the environmental. So, but I'm wondering, like, is there even from like experiment, like the experiment point of view, are people already doing these experiments, and is anybody like implementing it in like a pilot or large scale anywhere in the
Yeah.
world? Yeah.
Yeah, so that was actually a really fun part of this research was getting to look into industry and see what's being done. And there actually are a number of companies that are working in this space. So Blue Planet, for example, is a company that's doing pretty much exactly what we're proposing, which is using mineral waste, reacting that with CO2 to form these synthetic rocks for concrete aggregate. And they're in the process of building their first large scale commercial plant. So that's some potential. I think the carbonatable cements that I mentioned, those are more on the lab scale right now. The bio-based plastics, there are companies like Braskem that are already making bio-based PVC and bio-based polyethylene. So that's definitely reached sort of a commercial market. And there's also a company called Just Biofiber that's looking at using both biomass as well as carbonatable materials for bricks. I also found a company that was making the bio oil for asphalt as well. So there definitely are some companies. And honestly, since this paper has been published, it's been really fun to hear from a bunch of companies from around the world that I didn't know about that are also working in a similar space. And I can't remember names of some of them off the top of my head, but there's some that are just focused on the carbon capture part and trying to supply that CO2 to the concrete industry. There's another guy who reached out where they make bio aggregates. Not exactly sure what they do, but yeah, it's definitely cool to see sort of the interest on the industry side, because I do see it being like a really cool opportunity to shift to low carbon materials. And obviously there's a huge demand for them. So yeah.
So I'm wondering, like, is there any, with the carbon capture, there are different, like I said, the direct air capture or the capture from source. Is there any like what's the word now? Preference to how your carbon is captured?
So I think right now to make a technology feasible, utilizing existing CO2 sources from power plants, I think is the most straightforward. However, in order to really contribute to the climate targets, it would be even more beneficial to, I guess, on top of decarbonization efforts and, trying to reach net zero, taking CO2 from the atmosphere. Yeah.
Also, even thinking of like purity level, from like
Mm,
power plants and all, that would be like mixed with a lot of
yeah.
impurities, right? So I'm like, in your process, is there like a certain degree to
Hmm.
which the CO2 needs to be pure in order to put in these aggregates?
Yeah, that's a good question. Because we didn't look too much at the carbon capture side, I'm not sure what that process looks like for, like, for example, if you use flue gas. My hunch is that that is a more concentrated source of CO2 than just using CO2 directly from the air, which is why I think it has the potential to be easier to implement. But I don't know specifically like what that conversion process or like what's required for the pretreatment, I guess.
Follow-up question would then be, like you say, you guys didn't look at the capture part of things, but did you like include the emissions from like the capture process in your study?
No, so that's another great question. All we wanted to really look at is basically the magnitude of carbon storage potential, which is why when, for example, drawing comparisons of these materials to our traditional building materials, we didn't consider, for example, for like cement, we didn't consider any of the energy emissions associated with producing cement. We only compared these carbonatable cements to the chemical CO2 that's released from cement production. So we only compared process emissions, which for these carbon storing materials, all of those process emissions are literally just, net negative CO2. Whereas for cement, plastics, and the bio oil, or not regular bitumen oil for asphalt, all of those have some chemical stoichiometric emissions from processes. So we only compared those two. So we didn't look at any emissions associated with capturing the CO2 or converting it or pre-treating it. So obviously there could be a lot of emissions associated with those processes. Yeah.
Okay. So then I want to talk about, like you said, like it was really about the magnitude. So like in scale up, I know the title of your paper already says can capture more than 16 billion tons. So is that scaling up just one of the materials or like a mixture globally?
Yeah, so that 16 billion tons is reflective of global building materials and specifically looking at if we were to place all of our aggregates in concrete and asphalt with these carbonate-based aggregates, it's assuming that we replace all of our cement with these carbonatable cements and we replace 15% of that with these biochar replacement. It's assuming 15% of bricks made with biomass and also carbonatable bricks, a 20% increase in wood consumption, assuming all plastics that are used in construction are made with biomass, and using bio oil and bioasphalt. I think I got everything. But yeah, so it's basically looking at all of those materials. But again, 11 out of the 16 comes just from the carbonate-based aggregates used in concrete. I want to say another 2 billion comes from the carbonatable cements, and then the rest are all around 1 or less than 1 gigaton of CO2 storage potential.
Okay. And so it's this net. I'm still trying to this.
It's just, yeah, it's just looking at, basically it's just looking at the carbon content of these materials. So based on the mass ratio of carbon, what amount of CO2 can be stored in them. So it's not any process emissions or anything. It's literally just the carbon
Carbon
content.
content. So, but
Yeah,
like that's like the captured carbon or wherever source carbon. So it's like the carbon already in the system, right? Like you're capturing carbon to react, but like maybe for example, biochar also has carbon. Like so, you're not looking at just the source carbon that is like entering
right.
into the aggregate, but like the carbon in the entire building material. So
Yeah, so that's a good point. Yeah, so for like the carbonate-based aggregates, it is just the carbon content of the calcium or magnesium carbonates. For the cement, for example, the 15% of biochar, that's based on the carbon content of the biochar, and then the remainder is the carbon content of the carbonatable cements. So yeah, I think that's what you were saying. Yeah.
yeah. So, but like, how feasible is this? Like, I know you didn't look at economics and all, but like, when you're looking at the scale up, is this something that can be achieved, or
Yeah.
it's just a dream?
No, that was another thing that I was excited, what I was really eager to do when working on this paper is I was like, okay, it's cool to know sort of theoretically what we can do, but I also wanted to know like what could we do today and what's feasible. And so part of the study was also looking at how much carbon we could store in our building materials using resources that are available today. So if we just were to utilize, for example, mineral waste from mine tailings, steel, iron slag, waste concrete. So just looking at industrial sources of mineral waste, we could replace up to 10% of all of our aggregates with these carbonate-based aggregates. Again, assuming we have the technology to also react some CO2, which we do. It's just a matter of, investing more and making it more cost competitive. But if we were able to do that, we could store 1 billion tons of CO2 every year just in those concrete aggregates. And we also have enough agricultural residues to replace all of our bio-based plastics that we use in construction, as well as using biomass fiber in bricks, and biochar in cement. We looked at if we did all of those at the same time, we would have enough agricultural residues to supply that. And again, it's just a matter of making sure those value chains are created and sending those agricultural residues to the plastic manufacturers and the cement manufacturers. And then also creating some incentive for companies that already make these materials to switch to these low carbon alternatives.
Nice. So, like, what further research should be done in this area?
Well, I feel like we've sort of touched on some of them already. Obviously, the carbon capture side of things is pretty big. So making sure that's feasible. Also, like I said, we only really looked at the carbon storage side. So, and part of that is because the technologies are so new, it's hard to do a full LCA of what the process emissions might look like. But it would be great to do a full LCA and look outside of CO2 emissions at what the impacts might be. For example, if we want to access more of these minerals for the carbonate-based aggregates, that might require mining, which can have emissions such as particulate matter, which has human health risks. So really expanding the scope to look at alternative environmental impacts, I think, would be really important. And then also, I think doing an economic assessment, considering that there is so much interest from industry, I think having a robust assessment of, what criteria would have to be met in order to make this cost competitive, I think would be super valuable.
Awesome. Thank you, Elizabeth, for breaking down your study for us.
Of course. I'm happy to chat about it and glad there's interest.
Yeah, definitely. So, guys, thank you for watching. I'm going to be leaving the link to this study down in the description and also in the comment section. If you have questions, please ask in the comment section and I'll make sure Elizabeth answers.
Luckily, we work right next to each other. So.
Exactly. But yeah, until next time, continue to live consciously and I'll see you in my next episode. Bye. Thanks so much for listening to the Sustainability Nuggets podcast. I am Rarsu Marabi.
And I am Tosin Folorunsho. If you enjoyed this podcast, please leave a rating and review on wherever you listen to your podcast.
You can also show your support by signing up for a small donation to help sustain future episodes. You can find all relevant links in the description. See you in our next episode.